This will help to resolve key scientific issues, such as sea level rise, one of the largest unknowns in current climate models, that requires advanced ocean and ice sheet models for accurate future projections. The rapid changes that are occurring in the Arctic basin, especially the factors governing the recent rapid decreases in Arctic sea ice, and the impacts of an ice-free Arctic on global climate. The role of ocean mesoscale eddies on the global circulation of the ocean, and high-latitude biogeochemical interactions that include the potential for methane release, as well as the specialized ecosystems within the ice and at the ice-water interface. And our quay, Dr. Elizabeth Hunke, I congratulate you on the award of the 2017 Rothschild Lecture in the Rothschild Award in the Mathematics of Sea Ice Phenomenon, and now invite you to give the Rothschild Lecture entitled Large Sea Ice Modeling, Societal Needs and Community Development.
Thank you, Vernon. And I thank the organizers of this program and this workshop. This is a huge honor for me. I really appreciate it. I have spent most of my career developing this model, the sea ice model, which we now call CICE. We actually took a vote and did that, and Ed won to pronounce it CICE. I always pronounced it sea ice, C-I-C-E. The C was actually, I just pronounced it C, so it was sea ice. And the reason that I did that was because when I first started this back in the 90s, none of my friends had ever heard of sea ice. I hadn't heard of sea ice. And so when I told them that I was going to be working on sea ice, they were like, what? What is that? Sea ice? You know? And so that's what I named my model. So it's not an acronym. But now we're calling it CICE, the British way. So this has really and truly been a community effort right from the beginning. I didn't do it by myself. I could not possibly have done it by myself. And so some of that will come out in this lecture, but what has amazed me is that this model has become so popular and so successful over the years. And so one of the things that I thought about as I was putting this lecture together is why that is. What is it about the model that has made it so successful and so popular? So that's really what I want to get across today. And in this talk, because it's aimed at a general audience, I don't know that we have that many new people in this room, but apparently it's being live streamed, and there may be people listening outside who don't actually know what sea ice is. And so I'm going to give a bit of a primer about the physics of sea ice, and apologies to those of you who've seen that now, I think about 5 times today already. But sea ice physics and also for the sea ice modeling. And then talk a little bit about some new things that are happening, both in the physics and in the community. So first of all, sea ice is frozen seawater. That makes it very different from the ice that's on land, which is glacial ice. That's made out of snow, where it snowed on the land and compacted into ice. Sea ice is different because since it is frozen ocean, it contains a lot of things that are in the ocean, like algae and salt in particular. And that really affects the physics and how it behaves. Now this slide, some of you have seen multiple times, but the sea ice does exist and act on various scales, from the microscale, individual sea ice crystals, through blocks of sea ice, the flow scale from meters to kilometers, all the way up to the basin scale. And this is the scale that we as climate modelers are primarily concerned with. And this is the Arctic. You can see Greenland, Alaska, Russia over here. This is a very old image, I think SSMI, from probably the early 1990s. I've had this one around for a long time. But climate modelers, which is what I started out doing, can and do model things on smaller scales. But we have to do this very carefully. And we describe what's going on at these smaller scales in terms of the larger scale variables. sea ice does cover an extensive portion of the Earth. This plot is showing from 1988 in white the sea ice extent in the Arctic in the winter and in the summer where it melts back, and also in the Antarctic. The magenta line here is the median ice edge for 1979 through 2000. So it does not include the more recent years where the sea ice has been shrinking. But you can see that it does cover a large area in the winter months in the north and in the south. In general, sea ice covers about 4% of the Earth's total surface. I saw in your slide you said 10%, and I had to work that out. I think it's 10% of the oceans, right? 4% of the total Earth. But it's responsible for about 8% of the radiation balance for the whole Earth. And so it's kind of has an outsized role compared to the coverage that it has over the Earth. These plots are also of sea ice extent. In this case, it's the sea ice extent over the northern hemisphere in the month of September from 1979, which is the basically the beginning of the satellite record. There were some before then, through 2016. And in the Arctic, the sea ice extent has been decreasing. There were a couple of very unusual years in 2007 and 2012. And you see from year to year, there's a good bit of variability. In the Antarctic, there's also a lot of variability, but the trend has actually been going the other direction, upward. Scientists don't really understand why this is. They're still working on it. The last couple of years, it started going down again. We don't know what's going to happen there. But the point is that the sea ice does have horizontal extent, but it's also three-dimensional. It does have thickness. This is Steve Ackley out on the sea ice in the Wet LC, and you can see here's a ridge behind him. It's a smallish one, but as the ice converges, it does buckle and break up into blocks and form these ridges. So the sea ice does have a three-dimensional extent, but the thickness of the sea ice is very small in comparison to the extent of the sea ice. The aspect ratio is quite small. Sea ice is also moving around. We, as climate modelers, have been primarily interested in the large-scale motion of the ice, where here in the Arctic, for example, the ice tends to freeze over on the Asian side. It comes across the North Pole. Some of it goes out through France Strait. Some of it gets caught in the Beaufort Gyre and goes around. As climate modelers, this is the largest scale motion that we're interested in. But the sea ice is also in motion, let me see if I can get this started, at much smaller scales. And I love this video. It's gorgeous. If you have a chance, go out and look at the whole thing. We cannot, as modelers, begin to model this in global climate scale models. But we can watch the videos online, right? We do try to get the overall motion. Okay, so as the sea ice is moving around on the surface of the ocean, it's carrying things with it, such as soot, dust, and since the ice is moving from one side of the ocean to other areas, it's carrying this stuff with it. When it melts, it drops that into the ocean. That affects the ocean ecosystem. The sea ice itself has an ecosystem. You've seen this picture before today, but this is algae on the top of sea ice. In this case, it's an ice floe from the Antarctic that's tipped up on its side. The surface of it, which had a little bit of snow on it, has slid off so that you can see the layer of algae underneath. And then you can also see some algae in the interior of the ice floe. And so, as we're looking at this image, I generally ask the audience what's important. I've already given you one answer for this. Anybody else want to say, Don, don't say anything. As a clue. Yeah, well, we've already talked about it. What's important here for climate modeling is the albedo. It's the contrast, really, between the ice surface or the snow and the ocean, which is very dark. This absorbs heat, warms up the ocean. That heat from the ocean can help melt the ice. It makes the open water area bigger, and so you have a feedback loop. So that's the albedo feedback. But that's not the only thing that's important. If you're a biologist, you might care more about what the algae, what's going on with the algae, the chemistry in the ice. If you're an oil company executive, you might care more about the strength of the ice. There's lots of questions. But there is actually one other thing that climate modelers really care about. Anybody want to answer that one? Blue sky? Yeah, I like that. Well, it's actually the ice volume. Or since the ice has extent, you can think of this as the thickness. But the ice thickness is really important because it affects the rate at which the ice grows or melts thermodynamically. And also, in climate models, we've learned that you have to have the base state for your sea ice right in order to get your projections to look realistic. If you don't have the total ice volume right, you're going to get really lousy looking ice in, say, 2050 or 2100 when you're doing these climate runs. So let's talk about the modeling. As I said, one of the things that I wanted to do in this seminar is point out the reasons that I think my particular sea ice model has been popular. And that's CICE. What we modelers care about, of course, is we want to get the right answers for the right reasons. But there's a bunch of other things that we have to pay attention to in addition to that. So things like conservation. We have to conserve mass. We have to conserve water, salt, that's mass. We have to conserve energy. And here's a really important one. When you're doing climate modeling, you have to pay attention to computational efficiency. And I think what will come out in this lecture is that this has been a really important ingredient for our CICE model. We also want to be able to use the code for answering different kinds of questions without it crashing. So flexibility is important too. So first, let's talk about some of the ways that this model is used. Probably the biggest group of users that I have is CESM, the Community Earth System Modeling Project, which is based at NCAR. The Polar Climate Working Group within CESM has had a very long-standing and collegial collaboration to develop the sea ice model over the years. That's where a lot of it has happened. CESM users apply the model for many different things. Of course, CESM is used for the IPCC reports where you do century scale or even millennial scale simulations of the climate, going forward and also going backwards, looking at paleoclimate, climate variability and change. But these users also use it to look at individual processes within the coupled climate and just a number of things. Here's one of Ed's slides. He recognizes it. I stole it. Another user that we have here in the UK is the Met Office. They use the CICE model in their seamless forecasting suite, again, for forecasting the sea ice state, the climate state, the atmosphere, everything, on many different scales, from minutes right up through decades, and also climate on century scales. And they use it for many different applications, financial, resources, assets, all that kind of thing. Pretty interesting. This is a much broader use case than I ever imagined when I started modeling sea ice. I wasn't shooting for this at all. Another operational user, in addition to the Hadley Center, is the US Navy. And they have a couple of systems, one that's focused on the Arctic called ACNFS, Arctic Cap Nowcast Forecast System. And now they've expanded that into a global forecasting system, which they call GOFS, which includes both the Arctic and the Antarctic. they're forecasting the sea ice state and also the upper ocean state for the U.S. Navy's use. And in doing those forecasts, they're combining the sea ice model with an ocean model and also a data assimilation system. The Arctic products from this system are sent to the National Ice Center and to NOAA every day. The National Ice Center uses them to create their ice charts, which they send out to ship captains. And then NOAA uses it for the numerical weather forecasting that they do. Again, this is well beyond what I ever imagined my sea ice model would get used for. And the question has been raised already today, you know, at what point is the physics in that model actually not appropriate for these kinds of uses? That's a really good question, but I think there's a lot of really exciting work going on. We've heard some of it today, which will address those issues. In the meantime, the operational users are using what they've got. You know, that's the best they can do. So here's an example of one of the ACNF difference fields that's sent to the National Ice Center, and it's basically a 48-hour forecast of the change in the ice edge. So it's retreating in some places and expanding in other places. And you can imagine if you're a ship captain out there that knowing what the ice edge is likely to do in 48 hours might be pretty useful information. The Navy's also using it for some of their special missions and field campaigns. An example is a convoy back in 2011 that took a little over 10 million gallons of heating fuel to Nome, Alaska, because an unusual storm had come through and prevented their final shipment of fuel oil up to Nome. And they were going to run out in March. And Nome in March is not a place you want to be without fuel oil. So they used this model to forecast the sea ice conditions for this convoy of a U.S. Coast Guard ship and a Russian oil tanker to take that oil. They also use it for pre-flight planning for the Operation Icebridge missions and various other field campaigns. So let's talk about the physics a little bit. As I mentioned, the ice volume or the ice thickness is extremely important because it determines how the thermodynamics acts. So this is a schematic of the growth rate of sea ice versus the ice thickness. So we have thicker ice down here, thinner ice down on this end. And because the thermodynamic growth and melt rate goes as a function of the gradient, the vertical gradient of temperature, you have much greater variation in the growth and melt rates for thinner ice than you do for thicker ice. Now, the grid boxes that we use in climate models are pretty big. Like, say, 10 kilometers would be a really high resolution climate model. 40 kilometers, 100 kilometers, we don't run at that low resolution too much anymore. But those are still really big grid boxes, and so there's a lot of different ice thicknesses within those. And so we want to capture the variation in the growth and melt rates across those grid boxes. So what we do is divide up each grid box into bins, thickness bins. We call an ice thickness distribution. And this is a distribution in the mathematical sense. But in practice, in the climate models, we don't use very many bins. Typically we use 5. It's coded up, we can use any number. Some models use 12 or 20. We typically use 5, but we put most of them down here in the thinner ice area in order to catch that variability. So here's another schematic of what the ice thickness distribution looks like in the model for a 5-category thickness distribution. We have snow on top of each category, or maybe none. The amount of snow can vary. And then we also divide each category into layers for the thermodynamic calculation. We do a full thermodynamic calculation for each thickness category. And so what this means is that we're essentially resolving the thermodynamics within the grid box a little bit more by having various other thickness categories. And I'll also point out here that we're tracking the area fraction of each category. And you've seen this equation a couple of times before already, maybe 5 times before already. The ice thickness distribution equation is the fundamental equation in the CICE model. It's the one that ties everything else together, because any process that happens in the CICE or in the CICE model appears in here somehow. It affects the ice thickness, the ice volume. So what we have in here is lateral melting, and yes, this is your friendly community model. Chris said this, the friendly community model whose ice flows are all 300 meters in diameter. This is it, and that's the term. We have vertical thermodynamics, ice growth and melting. We also have divergence and convergence of the ice, and the mechanical redistribution, or what we call ridging. So we'll talk about the thermodynamics a little bit more. This ice thickness is influenced by various thermodynamic processes, including melting at the top and the bottom. We also can grow ice at the bottom, and we can grow ice at the top. And we do that by allowing the ice to flood either over the edges or percolating up through the ice. If it's cold, that liquid water can freeze, and that is snow ice formation. There's also the formation of frazzle crystals in the ocean that either accrete onto the bottom of the ice, or they can form a new layer of ice in open ocean. And then our thermodynamic calculation is now prognostic in salinity using a mushy layer approximation. By mushy layer, what we mean there is it's a mixture of both phases, the solid and the liquid phase of the material, in this case ice or brine. This is not actually sea ice, it's a proxy, but it's a pretty good one of some, we'll call them ice crystals, growing in a brine. And you can see as the ice crystals grow, there's a lot of liquid in between them. As the layer of ice forms, it's forming in an environment where there's very cold atmosphere above it and a relatively warmer ocean below it. So just because of that, because you have cold overlying warm, that would induce some convection within this mushy layer that's forming. But in addition to that, as the ice is forming, it tends to squeeze out the salt that's in the brine, because the ice crystals are pretty fresh. So the brine up here near the top, where it's cold and the ice is freezing faster, tends to be saltier than it is down here closer to the ocean. So again, the brine is heavier here, fresher. Both of these things together induce convection within the mushy layer as it's forming. So what happens is this heavy brine tends to flow out through channels in the ice, and then it forms plumes in the ocean. And meanwhile, there's relatively fresher, warmer ocean flowing upward. So you get this full circulation within the ice as it's freezing. Here's Ken's figure of X-ray tomography of actual sea ice. When it gets very cold, the brine that is left within this ice layer forms little tiny pockets of liquid brine. And then, when it starts warming up again, these little brine pockets start to coalesce. So you can see these two right here have joined, and they tend to do this vertically just because of gravity. Eventually, you have brine channels vertically through the ice. And I saw you showed this one. I stole this one off of your slides. Do what? Okay, well, I stole it off of your slides. So but anyway, this shows brine channels in a horizontal slice of the ice, so that you can see kind of it looks almost fractal to me, like a tree in the horizontal, and then in the vertical you can actually see the brine channels in these slices. So those features are fairly big. You know, this one right here is probably the size of my thumb, more or less. And, you know, I guess if you're slicing ice, that's a pretty big feature. If you're a climate modeler, that is not a big feature. There's no way that we can resolve that in a climate model. So we have to parameterize it. The way that we do that is with a set of equations that are based on fundamental physical principles like conservation of energy, conservation of salt. There's a liquidus relation for ice and brine, and this is describing the relative fraction of either liquid water or ice within your mushy mixture, which is based on temperature and salinity. So it's basically an equation of state. And then the last one, which we use to describe the velocity of the brine through the ice, is Darcy flow through a porous medium. So you put all those together and you have a fairly complex thermodynamics description, but we're also able to prognose the salinity. One aspect of this is melt ponds, which again have come up several times. Mainly they're referred to because they are a darker color than the surface of the rest of the ice. But in this case, they're really important because when the ice gets warm and those brine channels form, these can drain out. And as they're draining out, they're taking things with them. They're taking out the salt. They're taking out the algae and other inclusions. So they're a rinsing mechanism for the sea ice. Now, in addition to the thermodynamic processes, ice thickness is also influenced by mechanical redistribution or ridging, where you have two blocks of ice that are coming together. If there's enough force there to really force them together, the ice will buckle and break and form ridges on top and keels below the ice. So that's part of the dynamics of the ice motion. We describe the motion of the ice starting with a momentum equation. And there's a number of forcing terms here. One of them is the Coriolis term because the Earth is rotating. There's another one for the tilt of the sea surface. You know, sea surface is not completely flat and the ice just slides downhill. There are terms, surface stress terms for both the wind at the top of the ice and the ocean currents underneath. And then there's an internal stress term. And this one gets a little complicated. There's been a whole decades-long industry trying to describe the internal stress of sea ice because it's really hard to do. And that's what Veronique's talk was about. The classic way of doing this in a climate model is to use a viscous plastic rheology or constitutive law. And again, the classic way of describing the yield curve is an ellipse. We're still doing that. There are better ways. What I did way back when, I'm going to date myself now, is add a term to this constitutive law. And that simply added elastic waves into the model. So we have a Young's modulus, but we're not trying to physically model the elastic waves. We chose Young's modulus so that the time scale in the problem would be long enough that we could discretize it explicitly. And what that means is that the problem parallelizes really well. You don't have a lot of extra communication across processors. And so you can solve it really, really quickly just by adding this. Again, it's not physical, but it made the problem a lot faster. What amazes me is that this is EVP. You've heard a few times elastic viscous plastic. What amazes me is that EVP has just turned 20. I can't believe that, honestly. But it's amazing that it's still being used. I mean, this is really old technology. It's not that accurate. You know, there's lots of problems with it. People complain about it all the time. But it's still being used. And the reason that it's being used is because it's computationally efficient. So I'm really excited to see all the new physical parameterizations that are coming out. People are working on this. Just make sure you can do them fast, because that's what we need for climate models. coming back around to the ridging, once we have the motion of the ice, we can calculate where it's converging, where it's diverging. And when it's converging, it does form these ridges and keels. And typically, in the large-scale models, we do ridging just as the physical concept is that you convert the kinetic energy of the converging flows into the potential energy of the ridges and the keels. Pretty simple idea. It turns out that CICE is more complicated than that. And Andrew, who is here and will tell us about this on Wednesday, has started over on this problem from first principles using Lagrangian mechanics and borrowing some concepts from soil mechanics like an angle of repose. He is creating a completely new parameterization based on variational formulation. And the results that he's seeing are absolutely fantastic. I think the gray dots here are observations of ridges. We're plotting the angle of repose of the keel, I believe, with the shape. And what Andrew has found is that if, as in our usual models, if there's no pore space, cavities in between the ice blocks and the ridges, then you cannot get the observations. But if you allow the ridges to have those pore spaces, then you can do really well. And Andrew's going to say some more about this on Wednesday. I want to talk about the CICE ecosystem because this has been a really big thrust in climate models lately. And we've stopped calling them climate models, and that's not just because of our current president. It's because we really are doing Earth system modeling. We're including the atmospheric chemistry and the ecosystems in the ocean, and as part of that, we needed to include the ecosystems in the sea ice. It's a pretty complex problem. It's very tight coupling between the physical hydrological system and the chemistry and the biology that are in the ice. So at Los Alamos, and it's mostly Nicole Jeffrey, one of my colleagues, have created a full ecosystem model vertically through the sea ice. And not only that, coupled it to the ecosystem in the ocean. And doing that, Nicole has been able to reproduce the basic behavior of the ecosystems in the two hemispheres simultaneously. So in the Arctic, we tend to see algae growing at the bottom of the ice. And we see that in the simulations. In the Antarctic, like this picture, which is small here, but you've seen before, the blooms are actually happening at the top of the ice, in between the ice and the snow. We also see that with the same model. So it's able to capture that. But doing it is really, really complicated. I mean, there's just so much in an ecosystem. I've learned how to say, but probably not spell, phaeocystis. There's dissolved organic, nitrogen, carbon, different kinds of nutrients. There's just a lot of stuff here. And having this in the sea ice model means we have to carry it around. The ice is moving around. This is a tracer. These are all tracers in the sea ice model, and that can be really, really expensive. So here's another aspect of the model that I think has helped make it successful. And this was work that was done by Bill Lipscomb way back when, but he developed an incremental remapping scheme for the advection in this model. So what that means, if you have a conservation equation like this one for ice concentration, you can rewrite this very simple equation as this integral, simple time derivative. What that means is that you can figure out or calculate the amount of mass in your arrival cell just by adding up the amount of mass that's in a departure cell, which is defined by the velocity vectors at the corners. So that's all remapping is. You take the information that you had in this departure cell, which you can determine, and renormalize it for the arrival cell. It's very simple. And if your function that you're advecting is approximated as a linear function, then you get a nominally second order scheme. What's really cool about this is what happens when you have a tracer like this one. This is a tracer H. In this case it's thickness, so this equation describes conservation of volume. For those tracers, we've already done the geometry in order to calculate what the departure cell, where things are, how much stuff is in there, and so we can reuse that for the tracers. So this incremental remapping scheme has the usual properties that you want it to have, like being conservative and monotone, but also the tracers are very inexpensive. And this goes on, there's many layers. We have tracers being invected on top of other tracers. So for instance, I don't have the equation written out, but for conservation of energy, the tracer is actually enthalpy. So we have CHQ now in this equation, where Q is the enthalpy. And so we use in order to advect the enthalpy, we use the information that we got from these two equations. And it layers on. The biogeochemistry is the same way. And actually it gets even more complicated because the algae are actually living inside the brine pockets. They're not living inside the ice. So in order to advect these things, we need to know what the brine volume is. We get that from the salinity. We're calculating salinity. We advect the salinity now as a tracer, get the brine volume, and then algae and the nutrients and everything else involved with the ecosystem are advected with the brine volume, not with the ice. So that's just being able to do that is one of the things that this model is capable of that I think that a lot of other models may struggle with because of the advection. And I sat down and counted how many conservation equations we have in this model. If the ecosystem, the biogeochemistry is turned off, so we don't have that in there at all, we have 96 conservation equations that we're solving. That's just the CICE physics. When we add in the biogeochemistry, there's over 700 equations. So that's expensive, but that incremental remapping makes it possible. Okay, another really cool aspect about the sea ice ecosystem is that it feeds back on the physics of the sea ice. Because, the algae is dark colored, right? It would tend to absorb solar radiation. So we have kind of a fancy scheme for handling the solar radiation. It's a delta Eddington scheme, which is a multiple scattering parameterization, where the solar radiation comes in and it bounces off the surfaces in the ice. So we do have scattering layers. This is what Don talked about earlier. And eventually it goes down through the ice and a little bit comes out into the ocean at the bottom. We also have, let's see, there's different surfaces. The ice can have snow on it. It can have melt ponds on it. It can also just be bare, so that you just have the ice scattering layer on the top. That's 3 different surfaces, and we have those 3 different surfaces for each ice category. So we have 5 ice categories and 3 surfaces. We're doing 15 radiation calculations in each grid cell. So that, again, is increasing the resolution of the thermodynamic calculation. Beyond that, this is based on physical principles. So we're using measured values for what we call inherent optical properties. These are things like the extinction coefficient in ice and the single scattering albedo, the scattering asymmetry. Those are based on measured values. And then we calculate things like the albedo, the internal absorption, and how much radiation is transmitted to the ocean. It used to be that the albedo was a tuning parameter. It's not anymore. Our tuning parameters are, again, physical things like the snow grain radii. And there's lots of different ones, whether it's fresh or melting or non. But these are now the tuning parameters. But we can get some idea of whether the model is doing a good job because there are measurements for these too. So we can compare what we have to tune in order to get a reasonable simulation with measured values. Okay, so let's go back to the CICE model development. This is a list of things that I know of that have been developed in relatively recent years, including the salinity parameterization. There's a number of different melt pond parameterizations now. The snow modeling is getting better, biogeochemistry, all kinds of new rheologies, which is great. There's a lot going on. The nice thing about this is that as the models are getting more realistic, it is becoming easier for us to compare with observations, because what we're modeling is it's more like apples and apples comparisons. So some of the development that's going on at Los Alamos, well, there's a lot going on. We have a number of different CICE models now. There's the original one, the CICE model, but then we're also developing a new CICE model based on the MPAS framework. And MPAS stands for Model Prediction Across Scales. MPAS is based on an unstructured grid where you can put the higher resolution wherever you want it. You could put it in the Arctic if you wanted it. You can put it around the coast, under the ice shelves of Antarctica. You can put it in the Gulf Stream, wherever you want it. So this is being developed now. It's not been released yet, but it's getting there. And Adrian Turner is leading this effort. He is also developing a new discrete element CICE model, which is pretty cool. When he first said he was going to do this, I was like, what, are you crazy? Why are you doing this? Because I looked into this about probably 15 years ago or more and decided that it was not computationally feasible. 15 years ago, that was true, at least for climate modeling. And because it does cost a lot to calculate the interactions between all those little flows. But he's doing this now for the completely counterintuitive reason that it will be more computationally efficient than this one. And it is counterintuitive, but it's not because of any change in the physics or in the algorithms here. It's because of change in the computer architectures. The reason that the Department of Energy is going to an unstructured grid, and the reason for Adrian to start modeling using a discrete element model, is because the new computer architectures, which will be exascale speed, have like subcomponents in them. They're can't remember what they're called right now, K&L processors and things like that. Where you want to be able to take some portion of your calculation that's completely independent of everything else and move it onto those processors and just let it go. You can't do that with this style of model because there's too much communication. But with these, you might be able to do it. So that's what Adrian's trying to do. Another big important area of development at Los Alamos is the snow model. We're improving both wind redistribution, and for that we're borrowing the work from Olivier Lecomte in LIM. But we're also doing wet and dry metamorphism of these snow grains. And the reason for doing that is because we have that delta Eddington parameterization where the tuning parameters are the snow grain sizes. Well, now we're going to be calculating those, so the tuning parameters are going to be even farther down. But we're doing this based on the measurements, observations of the snow, and adding it to the basic model formulation, which includes standard things like, a standard thermodynamic model for melt and growth rates, conduction, radiation, turbulent fluxes, various ways of changing the snow mass through snowfall, sublimation, snow ice formation, and some of the snow is lost during ridging. We throw it off into the ocean. And in addition to that, snow is another one of those things that's getting advected around on the ice, so that snow is another tracer. Okay, now there's a lot of sea ice model development going on. I'm looking forward to learning more at this workshop about what's going on. So this is what I knew of when I put the talk together. There's, fast ice. Well, this is Andrew's ridging stuff. There's snow, flow size distribution, and there's probably more people out here. Wave ice interaction, icebergs. There's all kinds of things going on. And that's really exciting to me because it's really important to move this field forward. In addition to developing the sea ice model itself, there's also new developments in how to analyze the output. And an important part of that is that we're working more closely now with operational centers, because they can provide ground truthing for us, and also the data assimilation that they're doing provides skill information back to us from their data assimilation process. There's also new techniques in developing emulators for the observational data. I'll show you an example of that. And also uncertainty quantification techniques, both in developing new emulators and also skill metrics for the model. And I should mention, since Dirk is here, that there's also a big effort to standardize the history output for the CMIP 6 models. Okay, so this is an example of an observational emulator. Again, this is being done at the Naval Postgraduate School, but the difficulty has been that our model produces basically a snapshot of the entire Arctic at each time step that you put out the output. But the satellites are traveling in paths across the Arctic over time. And so it takes a certain amount of time to actually build up a full observation of the Arctic. And that means that you're not really comparing the same thing when you're comparing model output with the satellite observations. And so NPS has developed an emulator where it basically extracts from the model the same thing that the satellite would be seeing. So it flies a little satellite across in the model and picks up the data so that we can compare. Uncertainty quantification is a thread that passes through all aspects of climate detection, climate change detection, prediction, and also impacts analysis. And for decision makers, we need to be able to provide them the best information, and also some sort of assessment of how good of information it is. Uncertainty quantification is really important for us to be able to determine the significance of our results. And there's a lot of different tools in the UQ toolbox, and I've only listed a few of them here, but there are things like Bayesian techniques for risk analysis, again, reduced models and emulation, and also model hierarchies. So let me give a couple of examples of these. This is an example of using an emulator to better be able to better assess the skill or the results of a model. So in this case, we had two ensembles. One had 11 members, and the other one had 12 members. That's not very many members, but these are fully coupled models, and it's really expensive. You just can't produce that many ensemble members. And so what we did was use a statistical model to emulate the members of these two ensembles separately. And what that does, we essentially produced a pseudo-ensemble of 100 members for each one. And then using that, we can do robust statistics on it. So, for example, the thing that is different between these two ensembles is the amount of black soot that's in the atmosphere. Pretty small change, pretty difficult to say if you're looking at two maps. Well, this one's actually physically different from this one. It's really hard to do that. But we were able, using this technique, to say, yeah, these two ensembles are actually different for the first few years, And then after that, they're not different anymore. That's actually, believe it or not, useful information. Another UQ technique has to do with validating CICE models, or put another way, determining what the best parameter set is. So this is work that's done by my postdoc, Jorge Urrego Blanco, and he used the CICE model in a standalone mode and did an ensemble of 400 CICE runs. That's a pretty good sized ensemble, but he basically mapped out the entire parameter space for 40 parameters. And then the question is, okay, so which one of those is actually the best set of parameters? Again, it's pretty hard to say. What he did is develop and use a distance metric, which measures the distance between the model and the observations. And in doing that, he's using uncertainties in both of those. Because he has a 400-member ensemble of the model output, he's got basically uncertainty bars, variation on that. And then he has an ensemble of ice observations, including ice concentration, ice thickness, and various things from various sources. Put all that stuff together into a distance metric, and you get a skill metric, basically. So here's an example of comparing the model output with observed values of ice concentration. And he can find a parameter set where that actually looks pretty good. However, with that parameter set, the ice thickness looks terrible. I mean, this is the observations for the ice thickness, and this was the model output using this parameter set. And it's awful. You can find a different parameter set where you get the ice thickness in pretty good shape. But in that case, the ice concentration looks lousy. Okay? So what's nice about this metric is that you can optimize both of those at the same time. And in fact, you can optimize it across any number of observations simultaneously. So we could use ice age, various thicknesses. For the ice concentration, we're only showing the NASA team, but there's, I don't know, a dozen different ice concentration observation sets out there. You can use all of those and take into account the uncertainty across those. So now I want to say a little bit about the community work. The community development and collaboration has been absolutely critical for the development of the CICE model. And since the Department of Energy that I work for has embarked on the next generation development activity, we at first said, oh, well, we don't have enough cycle, there aren't enough hours in the day to support this model. And that kind of upset the community. They started yelling and screaming, and the Department of Energy, my program manager, actually listened. And so what we've done is, over the last year, is set up a consortium of community members. It's interagency and, in fact, international, to basically to maintain and continue developing the CICE model throughout the community. This consortium it formalizes long-standing collaborations that we've had with the research and development community, but it also makes explicit our connection to the operational users in our goal of accelerating the transfer of the new developments from the research and development community into the operations. So this is a schematic of how the consortium functions, or is intended to function, within the community. So the consortium is in the blue box right here. The research and development activities occur out in the community, not in the consortium itself. But the consortium enables those developments to get into the main code, progress through various confidence testing and code reviews and that kind of thing, and gets out on the public branches, and this is now in GitHub, so they're really accessible, where it goes back out into the community for the scientific testing and operational use, and then from there we can see that new developments might come online. So that's how it's supposed to work. And that has become a really kind of a different way of my working too, because I'm leading that effort now. So in summary, I hope you've gotten an idea. CICE is extremely complex, fascinating material, and it is very important for climate modeling, partly for the radiation balance, partly for freshwater flux, and also for the ecosystem. We're starting to realize that CICE is a critical part of the world ecosystem. These models, they're physically based. Although they were designed for very large scales, they're being used for very small scales. And also operationally, I think we need to look a lot closer at that, and I'm glad to see that there's a lot of new work being done to address the issues that come up in there. Something that I haven't really emphasized, I touched on it just for a short bit, is that we do have to make trade-offs as modelers. For the climate modeling, one of the most important concepts for us is conservation of mass, conservation of energy. You have to do that for long-term, centennial scale simulations. But for the operational centers that are doing data assimilation, they don't care about conservation at all. They're doing data assimilation. Oh, there's not ice there. There should be ice there. They just put ice in there. Okay. Conservation goes out the window. They don't care just because they're just running for a short period, maybe a week or two. So what you choose to do with the model really depends on the question that you have. And so in some cases, the model is not very good at this. It's not a very good assumption, but maybe the question that you're asking doesn't care about that. In all cases, computational efficiency is critical. We are moving to exascale computers. That's going to come online sometime in the near future. And what that means is not that we get to do more runs or longer runs. What it means is that the research and development community is like, oh, we can have more computing cycles. We can make the model more expensive. And so there's more and more physics going in. And so in order to still be able to solve the equations in these models, we still have to have computational efficiency. I think that is probably one of the most important things that has made the CICE model successful and popular. We did that by doing an explicit numerical formulation for EVP, and we also have this very efficient and accurate tracer transport in the advection equations using incremental remapping. And then, in terms of complexity, we are going to Earth system models with full biogeochemistry, and in order to do that, we needed to have a prognostic brine representation, the salinity, within the CICE model. And now that we've done that, we can feed back from the Earth system part of the model back onto the physical system. There's many new developments going on, both in the physical modeling and for analysis. I'm particularly excited about the possibilities for probabilistic forecasting and the use of reduced models like emulators. And finally, I'm 5 o'clock, and I'm going to just say that the best part of my job over the last 20 years has been working with the community. You guys are great. Keep doing it. Okay.
I think we'll adjourn now. We do have a reception to celebrate, so I think we can save the questions for outside and the congratulations for outside. So we have, hopefully, we have a reception outside now.